Hello friends, welcome to the session. Continuation of chapter 7, this DC to DC converters. Based on this chapter, in the previous sessions I discussed about what is the types of choppers based on output voltage level. Okay, that I discussed about buck regulator, boost regulator and buck boost regulator. And I solved some problems also. And I explained about what is the types of choppers based on quadrant operation. Type A, Type B, Type C, Type D and Type E choppers. Then what is the steady state analysis of Type A chopper, and based on that I solved some classroom workbook questions also. Then with respect to DC to DC converters, before starting the types of choppers based on commutation, first I want to discuss one small concept, that is a basic concept, that is concept of LC circuit or tank circuit. Okay, concept of LC circuit or tank circuit. Okay, that you concentrate. This important concept, this is a basic concept to understand commutation methods, to understand types of choppers based on the commutation. Okay, this is a basic concept. That is the concept of LC circuit. This, all of you note down this. Concept of LC circuit or tank circuit. This one important fundamental concept. The concept of LC circuit or tank circuit. Now, this concept I want to discuss in different cases. See under this case 1 I am discussing. Write down case 1. In this case 1, I am assuming that let the initial voltage across the capacitor is 0. The initial voltage across the capacitor is 0 and initial current through the inductor is also 0. There is no any initial voltage across the capacitor. There is no any initial voltage, initial current in the inductor. With this assumption, I am explaining this circuit. Let us consider this is an LC circuit. Let it may be thyristor or diode, or we also use diode. It may be thyristor or diode. Okay. Let the supply voltage is Vs. The supply voltage is Vs. And this is L and this is C. This L, this is C. Let current in the circuit is I. And there is no any initial voltage across the capacitor and there is no initial current in the inductor. With that assumption I am explaining. It may be, the circuit may be consist of diode or it may be consist of thyristor. Here in this circuit I am using unidirectional device. I am using one unidirectional device. It may be diode or thyristor. Let thyristor is triggered at alpha equal to 0 only. Okay. Now tell me. If the thyristor is conducting in this circuit, if thyristor is conducting, so what is the equivalent, you tell me? If thyristor is conducting, yes. Follow all of you. If thyristor, note down, if thyristor is conducting. Tell. If thyristor is conducting means, then apply the KVL for this loop. If you apply the KVL for this loop, what you can get? L into di by dt plus 1 by C integral I dt is equal to Vs. Correct? Now to find the equation for I and to find the voltage across the inductor, to find the voltage across the capacitor. If thyristor is conducting, inductor storing the energy, and there must be some voltage across the inductor. There must be some voltage across the inductor, and there must be some voltage across the capacitor. Yes, tell. Now, first I want to find the expression for I. For that, apply Laplace transform on both sides. Apply Laplace transform on both sides. Laplace transform on both sides. Then what you get to tell me? L into S. S into I of S minus IL of 0. Initial current in the inductor. With initial condition, I am applying Laplace transform. How to write Laplace transform, that you know. Plus 1 by C into I of S by S plus how to write 1 by C into I of S by S with initial conditions. With initial conditions, we are writing this equation. With initial condition, we are writing this equation. Okay. Then C into, we are writing 1 by C integral I dt. Na? For integration, we are writing this Laplace transform I of S by S. Then C into Vc of 0 by, you are writing Q expression. Q equal to CV. Na? C into Vc of 0 by S is equal to Vs by S. Note down this quick. I am writing this equation with initial conditions. In the capacitor, there is initial charge. Initial charge I written CV, Q equal to CV. That Q, or it is also written as Q of 0 by S. Q of 0 by S. Like that also you can write. That is 1 by C into I of S by S plus C into Vc of 0 by S is equal to Vs by S. S. Now tell. Then apply the initial conditions. What is IL of 0? 0. Then L into S into I of S minus 0 plus 1 by C into I of S by S plus 0 by S is equal to Vs by S. Then by simplifying this, what we get? Ls into I of S plus 1 by Cs into I of s is equal to Vs by s. Clear? Take I of s is common. What we get? LC s square plus 1 by Cs equal to Vs by s. This s cancel. Then from this you tell the what is the expression for I of s. Then I of s equal to C Vs by LC into s square plus 1. Yes. How to simplify this circuit that I am explaining. Then I of s equal to, take LC is common, C Vs by LC is common, s square plus 1 by LC. This you write. C cancel. Then what is I of s equal to 1 by L into or Vs by L into 1 by s square plus 1 by LC. Then to get one standard equation that I am writing here, I of s equal to Vs by L into divide by 1 by root LC multiplied by 1 by root LC s square plus 1 by LC I written 1 by root LC whole square. Then by simplifying this, I of s equal to this 1 by root LC, you write it into root LC. Root LC means root L cancel. Then what we can get? Vs into square root of C by L. Okay. By simplifying this one, we can get 1 by root LC by s square plus 1 by root LC whole square. Then apply inverse Laplace transform. Apply inverse Laplace transform. Laplace transform. Okay. If you apply inverse Laplace transform, then we can get the expression for I or I of t. The expression for I equal to, what is the expression? Vs into square root of C by L. Okay. A by s square plus a square. A by s square plus a square means inverse Laplace transform of a by s square plus a square is sin at. That means sin of 1 by root LC into t. Sin of 1 by root LC into t. Okay, this we can get. This expression for current in LC circuit. I equal to Vs into square root of C by L into sin of 1 by root LC into t. Okay. Yes. It is a LC circuit now. At XL equal to XC, there is a resonance condition may exist, but this generally 1 by root LC is resonating frequency. That's I am writing as angular frequency. 1 by root LC equal to omega naught. Then how we can write? I equal to Vs into square root of C by L into sin of omega naught t. Like this also we can write. Okay. This is in terms of 1 by root LC. It is in terms of omega naught. I equal to Vs into square root of C by L into sin of omega naught t, or I equal to Vs into square root of C by L into sin of 1 by root LC into t. Okay, this is the expression for current in LC circuit with supply voltage Vs without any initial conditions. That is, the initial voltage across the capacitor is 0. The initial current in the inductor is also 0. Once you know the expression for current, this is the expression for current. Now I want to find what is the expression for voltage across the inductor. How to write VL equal to L into di by dt. VL equal to L into di by dt. Then this L into di by dt, that is Vs into square root of C by L into d by dt of, that is sine of omega naught t. Then what we can get? Then VL equal to L into Vs into square root of C by L into sine omega naught t cos omega naught t into omega naught. Yes. Then what is VL? We can get L into Vs into square root of C by L into cos omega naught t. How to write omega naught? 1 by root L. 1 by root. Omega naught is written as 1 by root LC. This you write, simplify this one. VL equal to, this is root LC into Vs into Vs cos omega naught t into 1 by root LC. These two cancel. Then what is the voltage across the inductor? Vs into cos omega naught t. This is the voltage across the inductor. That means in a LC circuit, the voltage across the inductor is Vs into cos omega naught t. This is the case without any initial conditions. Yes. Now, once you know the voltage across the inductor, now you want to find what is the voltage across the capacitor. Then how to find voltage across the capacitor? Vc equal to 1 by C into integral I dt. This one method, or it is equal to, yes, this is VL, this is VC, this is VS. Shall you write VC equal to VS minus VL. Now from this one, VS equal to VL plus VC. Now what is I want? VC. VC I want means VC minus VL. This is another way to calculate. One method is you integrate, then apply the initial condition, then you find the expression for VC. That is one method. The another way to solve is you can calculate VC equal to Vs minus VL. Vs minus Vs into cos omega naught t. Then how you can get the expression for Vc equal to the voltage across the capacitor equal to Vs into 1 minus cos omega naught t. This is expression for voltage across the capacitor. Let this is equation 3 and this is the equation 4. The expression for voltage across the capacitor is Vc equal to Vs into 1 minus cos omega naught t. That is one expression. VL equal to Vs into cos omega naught t. I equal to Vs into square root of C by L into omega naught t. Clear? This note down quick. Okay. Now see, that means under the case 1, by simplifying this, what are the observations I am getting? That is in case 1, the expression for I equal to Vs into square root of C by L into sine omega t. Sine omega naught t. Then what is the voltage across the inductor equal to Vs into cos omega naught t. What is the voltage across the capacitor equal to Vs into 1 minus cos omega naught t. Okay. These three equations you remember. This is one observation. In this case, case 1, the voltage across the inductor and the voltage across the capacitor, and what is the current in the circuit. That means in this circuit, one observation is, therefore, the nature of the current is sinusoidal oscillations. The nature of the current is sinusoidal oscillations. Okay, sinusoidal oscillations. That is one observation. Sinusoidal oscillations. Where current is maximum at omega naught t equal to pi by 2 or t equal to pi by 2 omega naught. Omega naught is written as 1 by root LC, that is pi by 2 root LC. In terms of omega naught at pi by 2, in terms of t at pi by 2 root LC, I equal to IP, it is also called ICP, what that value? Vs into square root of C by L. This current is peak current, then this is ICP, that is Vs into square root of C by L. Substitute omega naught equal to pi by 2 here, then you can get the peak current. This is called peak current, it is also called peak commutating current. Peak commutating current. Why the name is given as a peak commutating current means, this circuit mainly is used as a commutation circuit. In many commutation method, forced commutation method, LC elements are used as a commutating circuits. That's the reason why whatever the current in the LC circuit, that current causes the commutation of the thyristor. That's the reason it is also called peak commutating current, or it is also called peak current. Once you know the peak current, then you also write what is expression for I equal to the instantaneous value of I equal to IP into sin omega naught t. Then at omega naught t equal to pi at omega naught t equal to pi by 2, current becomes maximum. Then what is that I equal to IP equal to Vs into square root of C by L. Then in general, how to write I is also equal to IP into sin omega naught t. That means instead of writing here, this I is also written like this. This also equal to IP into sin omega naught t. Also write like this. What is omega naught here? Where omega naught equal to 1 by root LC. Okay. Omega naught equal to 1 by root LC. This is one observation. Where the current is 0. In this circuit, where the current is 0. Yes. Tell. At omega naught t equal to, one more observation, at omega naught t equal to pi or t equal to pi by omega naught, that is pi root LC. In this circuit, the current is 0. At omega naught equal to pi, current is 0. Then I equal to 0. That is the second observation. Tell me. At omega naught equal to 0, at omega naught equal to 0, what is voltage across the inductor? VL equal to Vs. Voltage across the capacitor, Vc equal to Vs. Substitute here. At omega naught t equal to pi by 2, then what is VL equal to 0? What is VC equal to? At omega naught t equal to 0, at omega naught t equal to pi by 2, at omega naught t equal to 0, that is, what is this one? VL equal to Vs. Then VC equal to how much? Omega naught t equal cos 0, that is 0. VC equal to 0. This is Vs. Tell me, at omega naught t equal to pi, what is VL equal to? Minus Vs. VC equal to 2 Vs. Okay. Then with this observation, different observations I am giving here. Okay. Different observations I am giving here. Different observations I am giving. Say this. Now, that means in this LC circuit, current is maximum at pi by 2. Omega t equal pi by 2 or t equal pi by 2 root LC. Current is 0 at omega t equal to pi or t equal to pi root LC. What is the voltage across the inductor at omega naught t equal to 0? What is the voltage across inductor and capacitor at omega naught t equal to pi by 2 and omega naught t equal to pi? Then with this observation, if you draw the characteristics, what we can get? Tell. I am drawing the current and voltage expressions. I am drawing the current and voltage waveforms. Let this is I waveform. The nature of the current is sinusoidal and the current is maximum at omega naught t equal to pi by 2. 0 at omega naught t equal to pi. This I am writing in terms of omega naught t. If you draw these waveforms with respect to t means, here you take pi by 2 root LC, this is pi root LC. Then what this maximum value? This maximum value of current is, yes, this maximum value of current is Vs into square root of C by L. Here we are getting only positive sinusoidal oscillation. We don't get any negative sinusoidal oscillations. Even though nature of the current is sinusoidal, in this circuit we don't get any negative sinusoidal oscillations because I consider only unidirectional device. If you don't take this unidirectional device, but in this circuit the nature of the current is bidirectional current we can get. Okay, then this is the only unidirectional oscillation only we can get. Then if you draw the voltage across the inductor waveform, this is VL waveform. If you draw the voltage across the inductor waveform means, then what we can get? For omega naught t equal to 0, VL equal to Vs. This VL equal to Vs. For omega naught t equal to pi by 2, VL equal to 0. And this is VL equal to minus Vs. Then you draw the voltage across the capacitor waveform. Draw the voltage across the capacitor waveform. This also omega naught t axis, omega naught t axis. If you draw the voltage across the capacitor waveform means, at omega naught t equal to, this is 0. This is plus Vs. This is 2 Vs. Then you get the wave shape like this. That means with initial conditions are 0, the voltage across the inductor is changing from plus Vs to minus Vs. That means with IL of 0 equal to 0, Vc of 0 equal to 0, if omega naught t changing from 0 to pi, then voltage across the inductor is changing from plus Vs to minus Vs. Voltage across the capacitor is changing from 0 to 2 Vs. The point to remember, capacitor charged to a maximum voltage at omega naught t equal to pi, and it charged to a maximum voltage of 2 Vs. That means without any initial conditions, capacitor charged to a maximum voltage of, the point to remember, this is the voltage across the capacitor. Capacitor charged to a maximum voltage at omega naught t equal to pi. Without any initial conditions, any initial voltage, capacitor charged to a maximum voltage of 2 Vs. Capacitor charged maximum of 2 Vs. Without any initial voltage, capacitor charged to maximum of 2 Vs. Capacitor charged to maximum voltage at omega naught t equal to pi. These points you remember. This is case 1 observation. Under case 1, what is the current in the circuit? What is the voltage across the inductor? What is the voltage across the capacitor? Then what is the observations? This is important. Clear? Okay? Not all. Quick. Yes. Can you tell me, if it is capacitor is fully charged, at that condition, the voltage across the thyristor equal to, at steady state condition, that is, if the capacitor is fully charged, one more point you write, if the capacitor is fully charged, that is, the voltage across the thyristor equal to the voltage across the thyristor equal to how much? Vs minus, at steady state condition, the voltage across the inductor is Vs minus VL minus Vc. But at steady state condition, inductor acts as a short circuit. Then what is the voltage across the thyristor? Vs minus 0 minus 2 Vs. Then the voltage across the thyristor equal to minus Vs. The voltage across the thyristor is minus Vs means this thyristor is commutated. Okay, this is happening, all this happening at omega t equal to pi plus. That means at omega t equal to pi plus, pi or pi plus, at the instant of pi plus, capacitor charged to a voltage of 2 Vs. Inductor acts as a short circuit. Once it is fully charged, inductor acts as a short circuit. Then this is Vs minus 0 minus 2 Vs. At the instant of pi plus, the current in the circuit is 0. When the current in the circuit is 0, then the thyristor is commutated. Understood? That's why in LC circuit, thyristor is commutated, because the nature of the current is sinusoidal oscillations. At a particular instant, current is 0, then thyristor will be commutated. Okay. Then when it is commutated means at steady state condition, Vt equal to Vs. Then at steady state condition, what is the voltage across thyristor equal to voltage across the Supply voltage minus voltage across the capacitor. Understood? That statement also you remember. Okay, this is about case 1. Now we concentrate on case 2. See the case 2. Here I don't want to give the derivations, follow the same, whatever the I given starting derivation, how to apply the Laplace transform, how to apply the inverse Laplace transform, all these you know. Now with this knowledge, directly I am writing the expressions. Is this okay? Yes. Tell. Under case 2, let Vc of 0 equal to V0. Actually it is a plus V0. V0 means positive V0. The initial voltage across the capacitor is positive voltage. Then the initial voltage, initial current in the inductor is 0. Still it is 0. Then by analyzing this, apply Laplace transform and inverse Laplace transform, whatever the previous I given, but the initial conditions you substitute. But in that equation previous case, I substituted initial condition, both are 0. But you substitute the initial condition, then you see the expression. Okay, directly I am writing. Then the current I equal to Vs minus V0 into square root of S. C by L into sin omega naught t. I equal to Vs minus V0 into square root of C by L into sin of omega naught t, where omega naught equal to 1 by root LC. That is fixed. This is the expression for current with initial voltage across the capacitor. Here the initial voltage across the capacitor I taken positive. That's why this I am getting, by simplifying you can get minus. Simply you remember like this. If the initial voltage across the capacitor is negative, then you take this is plus. This is positive, then you can getting this one. If it is given as a minus, minus of minus it becomes plus. Then you can get the expression. Understood? Now tell. Then what is the voltage across the capacitor? The voltage across the capacitor equal to Vs minus V0 into the voltage across the capacitor equal to Vs minus V0 into cos omega naught t. And this is the voltage across the capacitor. The voltage across the capacitor equal to Vs minus V0 into cos omega naught t. Yes. If you substitute V0 equal to 0, Vs into square root of C by L into sin omega, you get previous expressions. You substitute V0 equal to 0, Vs into 1 minus cos omega naught, we can get the previous expression. Okay, this is about, if it is given as the initial voltage across the inductor capacitor is given as a negative voltage. If it is negative voltage means, then you take this is the plus, because minus into minus it becomes plus. This I given with the assumption of positive voltage. With the assumption of positive voltage. Okay, this is about the case 2 condition. Now see, in this circuit, if it is a source free LC circuit, this I am giving this. In this I am giving, if it is source free LC circuit, in case 2 itself, if it is source free LC circuit, source free LC circuit, if it is a source free LC circuit, then how we can write? Source free LC circuit means if it is given like this. This is a switch. The initial voltage across the capacitor is Vc of 0. That is, initial voltage across the capacitor is plus V0. This is equal to Vc of 0. That is a positive voltage. Yes. Then in this case, then how to write I equal to? In this expression you substitute Vs is 0. Then what we can get? Minus V0 into square root of C by L into square root of sin omega naught t, where omega naught equal to 1 by root L C. Then how to write what is the voltage across the capacitor equal to? Substitute Vs is 0. Then what we can get? Plus V0 into, substitute Vs equal to 0. This is 0. This is also 0. It's correct. Then this is also 0 means, then what we can? Plus V0 into cos omega naught. This is voltage across the capacitor. Here I taken Vc of 0 equal to initial voltage across the capacitor equal to positive. If you take this is negative, initial voltage across the capacitor is negative, then it is taken as a plus, then it becomes minus. Yes sir, this becomes minus of minus plus, plus into minus, this becomes minus. Sir, how to say that? If it is not mentioned, if it is the initial voltage across the capacitor is positive or negative, if it is not mentioned, then how to say that it is not mentioned, is a positive voltage or negative voltage, how to say that? For example, if it is LC circuit, the direction of current is like this. If it is given that plus V0, then with respect to current direction, the polarity is given like this, plus minus. The given polarity is also plus minus. Then you take Vc of 0 equal to plus V0. For example, if it is given like this, the initial voltage across the capacitor is V0, it is given. Then the direction of current is like this. The direction of current is like this. According to current direction, this is plus minus. But what this polarity? Minus plus. It is opposite now. Then you take Vc of 0 equal to minus V0. Like, if it is not mentioned, the voltage across the capacitor is positive or negative, like that it is not mentioned, then by seeing the circuit, how to identify it is a positive voltage or negative voltage? Based on the direction of current in the circuit, then we can identify positive voltage and negative voltage. Understood? Can identify positive voltage and negative voltage. Okay. Now this is source free LC circuit. In source free LC circuit also, the nature of the current is sinusoidal oscillations. Nature of current is sinusoidal oscillations. Nature of current is sinusoidal oscillations. Sinusoidal oscillations. Nature of current is sinusoidal oscillations. Okay. Now if you draw this current, then you can get like this. It is also sinusoidal current. This is omega naught t. At omega naught t equal pi by 2, it is maximum. This is pi. At omega t not equal to pi. Then if you draw the voltage across the capacitor, means, then you can get the expression waveform like this. At omega naught t equal to 0, it is plus V0. This is plus V0 to, this will change us like this. This is plus V0 to minus V0. Plus V0 to minus V0. At omega naught t equal pi by 2, it is 0. At omega naught t equal to pi, it is minus V0. If you write the voltage across the inductor, we can get, this is the voltage across the inductor equal to minus V0 into cos omega naught t, you can get. Then if you draw the voltage across the inductor waveform is like this we can get. If you draw the voltage across the inductor waveform. Minus V0 to plus V0. This is voltage across the inductor. This is plus V0. This is minus V0. This I am drawing these waveforms with respect to initial voltage across the capacitor is positive. If you take initial voltage across the capacitor is negative, these two waveforms will be reversed. Then capacitor voltage charge like this, then inductor voltage falling like this. But this is plus, this is Vc plus V0 minus V0, VL is minus V0 plus V0. Okay, this is the source free LC circuit. These two cases I discussed till now. Case 1 is we don't have any initial voltage across the capacitor. If there is initial voltage across the capacitor, then what is this voltage? I, this is Vc equal to Vs minus V0. See, we know that capacitor charged to a maximum voltage of omega naught t equal to pi. At omega naught t equal to pi, what is the peak voltage across the capacitor? Peak voltage across the capacitor. Cos omega naught t pi. Cos pi minus 1. Minus into minus plus. That what you can get 2 Vs minus V0. 2 Vs minus V0. At omega naught t equal to pi, Vcp equal to Vs minus V0. If it is 2 Vs minus V0 means, now what is the voltage across the thyristor? Vs minus 2 Vs minus V0. Then the voltage across the thyristor is minus 2 Vs plus V0. Then what we can get? This is 2 Vs minus V0 na? Yes. Minus 2 Vs plus V0. Then what we get? Minus Vs plus V0. Okay. Like this we can. This is the voltage across the thyristor. Okay. Can you find what is the peak current in this circuit? The peak current in the circuit at omega naught t equal to pi by 2, it is peak current. Then what is Ip equal to Vs minus V0 into square root of C by L. This is the peak current. At omega naught t equal to pi by 2, current is maximum na. That's why this is the peak current. Vs minus V0 into square root of C by L. That means simple observation. You see, if the initial voltage across the capacitor is positive, to get peak current, if it is given as positive, then you subtract from Vs. If the initial voltage across the capacitor is positive, without initial voltage, capacitor charged to a maximum voltage of 2 Vs. If it is plus is given, you take minus. If it is minus is given, you take plus. Easy to write. Okay, this is about 2 cases. In remaining cases, in the next session, I will continue. Okay, understand?